Welcome to the Deep Dive. Today, we're plunging headfirst into, well, one of the biggest environmental villains of our time, plastic waste.
Yeah, it's a massive topic.
It really is. And we're not just talking any plastic. We're zeroing in on polyethylene terephthalate, PE.
Right, PET, the stuff in soda bottles.
Exactly. Or that's what you might think. But here's the surprising bit. PE is, well, it's absolutely everywhere. It makes up a staggering 83% of the fiber market.
83%, wow.
Yeah. So that means it's woven into a huge amount of the clothes we wear every single day. And, with the relentless rise of fast fashion, we're facing this unprecedented flood of textile waste.
It's piling up.
It really is. And this isn't just an environmental nightmare. It's creating real economic pressure, too. It's forcing us to find radically better recycling solutions for these materials.
And that search for truly effective solutions is, well, it's complicated. The current PE recycling methods have real limitations.
Like what, for example?
Well, take mechanical recycling. It works okay for simple things, like clean bottles, maybe.
Okay.
But it's got significant drawbacks. You often end up with a loss of quality. We call it downcycling.
Right, downcycling.
Meaning the plastic becomes weaker, maybe discolored, just not as good. And crucially, it's largely useless for complex materials.
Like those blended fabrics.
Exactly. Those blends we see everywhere today. Mechanical just can't handle them well.
Okay, so what else is there? Chemical recycling.
Then you have traditional chemical recycling. Now, it can produce material that's essentially virgin quality, which sounds fantastic.
It does.
But it often demands incredibly harsh conditions. We're talking temperatures over 180 degrees Celsius.
Whoa.
And using toxic or flammable chemicals. So yes, it's effective, but at what environmental cost? Or safety cost? It's not exactly a green process,
Right. So we're faced with this massive problem, and the current solutions are either, limited or they come with their own heavy baggage.
Pretty much.
But what if the solution wasn't in brute force, but in, tiny biological architects, engineered to gently dismantle plastic piece by piece?
Now you're talking enzymes.
Exactly.
Okay.
Today we're diving into a truly fascinating new approach, enzymatic depolymerization. Our mission here is to unpack the cutting-edge research that's significantly boosting these enzymes' capabilities.
Especially for those blended fibers.
Especially for those notoriously difficult blended fibers that our current methods just, can't seem to handle effectively.
Yeah.
It's a story of science tackling one of the planet's biggest puzzles.
It really is fascinating stuff.
So to really grasp the scale here, let's zoom in. Why is peat such a tough challenge?
Well, beyond the sheer amount of it.
Yeah, the volume is huge, but why is it so widely used?
It's incredibly versatile. It resists heat, abrasion. It's a great gas barrier, keeping the fizz in your soda.
Right, so it's good stuff, functionally.
It is. But here's the kicker. Textile consumption alone is projected to increase by a massive 50% by 2030.
50%.
Yeah. Think about that.
Yeah.
Half again as much textile waste potentially coming down the line.
We just can't keep going the way we are, landfilling this stuff. The pressure on resources, the emissions from production, it's just unsustainable.
Totally unsustainable. And when we talk textiles, those blended fibers, PE mixed with cotton or maybe starchy polyurethane, they're the real recycling headaches.
Why are they so much harder?
You can try to separate them mechanically, but it's like trying to untangle, hopelessly knotted strings. It's just really inefficient.
Okay.
The holy grail for high-quality recycling is selective chemical degradation, basically dissolving just the PT. That offers far greater material purity.
Makes sense.
But actually isolating the PE effectively from these composite materials is one of the most challenging tasks in recycling today.
And that brings us back to the problems with traditional chemical methods, right?
Exactly. Those environmental drawbacks become really glaring. As you said, they often guzzle large quantities of toxic, flammable reagents.
Right.
It works, sort of, but it's like using a sledgehammer when you need a scalpel, a very specific scalpel at that.
Which brings us neatly back to enzymatic depolymerization, this really promising and hopefully environmentally friendlier alternative.
Yeah, the potential is huge.
Where are the key advantages then?
Well, the big ones are it operates at much lower temperatures, typically below 80 degrees Celsius.
Okay, much cooler.
And at neutral pH, basically in watery conditions. No harsh chemicals needed for the main reaction.
That sounds like a giant leap towards, green chemistry.
It really is. It offers this gentle surgical approach where brute force just wasn't cutting it or was too damaging.
So what exactly are these biological scalpels, these enzymes?
They're called PET hydrolases. You can think of them as tiny, highly specialized biological scissors.
Okay.
They come in a couple of main families, some originally found in fungi, others in bacteria, and they all share a similar, unique 3D shape and a specific molecular sweet spot. Scientists call it a catalytic triad.
That's where they do the cutting.
That's where they do their cutting work, yeah. A bit like other enzymes that break down fats or proteins. And fun fact, some of the very first enzymes found to degrade PET fibers were actually cutenases.
Cutenases, what do they normally do?
They normally break down cutin, which is the waxy layer on plants, so it was a bit of a surprise discovery.
Huh. So, okay, these enzymes exist, they have this potential, but you mentioned earlier they weren't perfect. What was holding them back in the early days? What were the roadblocks?
Right. That's where it gets really interesting. Despite all the promise, the early sort of natural enzymes faced two major challenges.
Okay.
First, they were just too slow, like really slow. Imagine trying to empty a swimming pool with a teaspoon.
Okay, not practical for industry.
Not at all. And second, and this is crucial, they couldn't effectively reach all parts of the plastic, especially the tightly packed crystalline regions of PT.
Crystalline regions, like the really dense bits.
Exactly. Imagine trying to eat a giant block of ice, but you can only nibble at the edges because the middle is rock hard and tightly packed. That was kind of the challenge for these early enzymes.
Gotcha. So slow and couldn't get to all the plastic.
Precisely. But scientists have been working tirelessly on this. There are some well-known engineered variants out there now.
Like which ones?
Well, one prominent example is LCC-ICCG. It comes from a leaf and branch compost cuteness.
Okay.
And it's shown impressive performance breaking down a good chunk of peat, maybe 90% in some tests in just a few hours. But it needs quite specific conditions, like 72 degrees Celsius.
Still pretty hot then.
Still fairly hot, yeah. Other notable players include variants derived from that famous plastic-eating bacteria, Iidinella sakiensis. You might have heard of ispatase.
Vaguely, yeah.
So variants like phaspatase and turbopatase came from that. LCC-ICCG has generally been seen as a strong performer, though some studies showed turbopatase had higher activity against pre-treated PD bottles, but at 65 degrees. So, there's this ongoing race to find the real champion enzyme.
And that brings us to the new contender in this race, PT2. This is the focus of the study we're diving into.
That's the one.
And its origin is quite surprising, right? It wasn't originally known as a plastic eater.
Not at all. It was first identified as a lipase, an enzyme that breaks down fats. Only recently was it recognized as a PT hydrolase 2.
Huh. And there was an earlier tweaked version.
Yeah, PT2-7MA. It had 7 mutations, showed about 3 times higher activity than the original wild-type PT2, which sounds good.
Nice.
But, and this is important, even that improvement was still considered pretty insufficient for practical real-world use. It was promising, sure, but not quite a game changer. Not yet.
Okay, so PTT7M was better, but not enough. So this new research, they set out to really supercharge it.
Exactly. And this wasn't about just one lucky mutation. It was about a really systematic, almost strategic approach to engineer PT2 for significantly higher activity.
How did they do that?
They used a multi-pronged attack, combining what we call random mutagenesis.
Like trial and error.
Sort of, yeah. Introducing mutations broadly, like throwing darts at a board, hoping some hit the right spot. But they also combined it with site-directed mutagenesis.
Which is more targeted.
Much more targeted. Precisely changing specific points in the enzyme's structure. The goal was to refine both the enzyme's surface, how it interacts with the plastic, and its active site, the cutting machinery itself.
Okay, so a combination of broad searching and precision engineering.
Yeah.
How did they start? With the surface?
Yeah, they started with the surface. Think of it like upgrading a car's tires and aerodynamics first.
Okay.
They found 7 new beneficial mutations through that random screening process. Some were quite clever, like L103K, which added a positive charge to the surface that interacts with PT.
Helping it stick to the plastic.
Exactly, like adding tiny molecular magnets, because PT has negative charges. Others, like G76 and A144C, created a new internal bond, a disulfide bond.
What did that do?
It acts like molecular rivets, basically holding the enzyme together better, increasing its stability, making it tougher, more robust, especially at higher temperatures.
Okay, so stickier and tougher. did they combine these?
They did. They created a variant called PT2K7 with just those 7 new mutations. It showed over 8 times higher activity than the original PT2.
8 times. That's a big jump.
It is. And then they combined that with the tweaks from the earlier PT27M variant. That created PT214M with 14 mutations in total.
And how did that perform?
That pushed the activity to almost 9 times higher than the original. What's really cool is that these surface mutations effectively created a larger, positively charged patch on the enzyme, making it much, much better at binding onto the plastic surface.
Okay, so they seriously upgraded the enzyme's grip and its stability. But they didn't stop there, did they? You mentioned refining the surface and the active site.
Right, they kept going. They further modified the surface by introducing 2 more mutations, Y55S and A264R, into that PT214M variant.
By those 2.
These were designed to further optimize that positive charge on the surface, actually making it look a bit more like that highly efficient ispitase enzyme we mentioned earlier.
Learning from other successful enzymes.
Exactly. And it subtly increased activity even more. Interestingly, these last 2 slightly decreased the enzyme's thermal stability, but it didn't really matter because it didn't impact the reaction at their target temperature of 60 degrees Celsius.
Okay, so surface optimized. Then they turned to the business end, the active site.
Absolutely. Once they had a really robust enzyme with a great grip, they focused on the active site, where the actual PT cutting chemistry happens.
How did they approach that?
For this, they used another high-performing variant called hot patase as a kind of structural blueprint. They essentially looked at what made hot patase so good at cutting and tried to mimic it in PT2.
Smart. Reverse engineering success.
Pretty much. They identified 6 key amino acid residues, the building blocks, right around the catalytic center of their PT214M enzyme, and they carefully modified them to match the ones in hot patase.
And the result?
The result was a new variant they called PT214M6 hot. And this modification led to another significant jump in performance. It produced more than twice the amount of breakdown products compared to PT214M.
Wow, so doubling the output just by tweaking the active site based on another enzyme.
Yeah, it really shows the power of precision engineering right at the molecular level.
Okay, so surface mods, active site mods. Was there a final step? Did they put it all together?
There was. The final sort of breakthrough step was to strategically combine all these upgrades. They further optimized those 6 active site mutations and integrated them with all the successful surface modifications they had already achieved.
This sounds like the turbo button moment.
It really was. This meticulous, multi-step engineering process led to the creation of PT221M, a variant with an incredible 21 mutations in total.
21 mutations. And the performance.
Truly remarkable. It demonstrated a 28.6-fold increase in the concentration of total product compared to the original wild-type PT2.
28.6 times. That's huge.
It's a massive increase. To put that in perspective, while translating lab results to factory speed involves many factors, this headline figure points to unprecedented efficiency.
Meaning you could use less enzyme. Make it cheaper.
Exactly. It means we can potentially break down a huge volume of plastic with a much smaller amount of this enzyme, making the whole process far more economically viable and scalable than anything we'd seen before with PT2. It really moves this from a lab curiosity towards being a real industrial contender.
And they measured the specific products, the building blocks.
They did. They were getting significant yields, like 11.6 millimolar TPA and 22.4 millimolar MHET from PET powder. Those are the valuable monomers you want to recapture and reuse.
Okay, so this is a monumental leap in the lab. Really impressive science. But the big question always is, what does this mean for the real world? Scaling up enzyme production could be a bottleneck, right?
Absolutely. That's often the sticking point. But the researchers address this head on. They established a highly efficient enzyme production system using a common industrial workhorse yeast, Comagatella fafi. You might know it by its older name, Pichia pastoris.
Oh yeah, that's used a lot in biotech.
It is. They meticulously optimized the cultivation conditions, temperature, feeding strategy, everything. And they managed to achieve a really high yield. Up to 691 milligrams of PT214M6 hot per liter of culture after about 137 hours.
Is that good? 691 milligrams per liter.
That's a really promising output for potential industrial scaling, yes. It suggests producing large quantities is feasible. Interestingly, they got the best yield at 23 degrees C, which is lower than typical yeast production temps. They think maybe better oxygen solubility at the lower temp helped.
Okay, so production looks feasible. What about performance? You mentioned the head-to-head tests.
Right, the critical large-scale degradation tests, the real showdown. They put the best variant, PT221M, against that established enzyme, LCC-ICCG.
Using real plastic.
Using powdered commercial PT bottles, yeah. A more realistic scenario than pure lab chemical.
How did PT221M stack up?
Well, the comparison reveals some interesting nuances, and PT221M's significant advantage, especially in efficiency.
Okay.
At a typical setup, say 20 grams of PT per liter and 5 milligrams of enzyme per liter, PT221M completely degraded 95% of the PET within 24 hours. And that was at a moderate 60 degrees Celsius.
95% in 24 hours. How did LCC compare?
LCC-ICCG actually achieved 91% degradation faster, in about 10 hours, but it needed that higher temperature of 72 degrees Celsius.
So faster but hotter for LCC. PT221M is a bit slower but works at a lower temp.
Right, but here's where PT221M really shone, when they halved the enzyme concentration using only 2.5 milligrams per liter.
Making it potentially cheaper.
Exactly. PT221M still degraded a significant 50% of the PET in 24 hours. LCC-ICCG, at that lower concentration, only managed 26%.
So PT221M is much more efficient when you don't use as much enzyme.
Precisely. It highlights its superior efficiency at lower, more economical enzyme loadings. You need less of the expensive stuff to get the job done, potentially.
That seems like a big deal for industrial use.
It is. And it also brings up that interesting point about temperature. LCC-ICCG works at 72 degrees, which is above PET's glass transition temperature to use.
The point where it softens.
Yeah. But at that temperature, the PET can also start to recrystallize, kind of stiffen up again in places, which can actually compete with the enzyme trying to break it down.
Oh, right. So the heat helps, but also potentially hinders.
It can. The lower temperature used for PT221M, 60 degrees Celsius, might actually lead to more complete degradation in the long run by reducing that unwanted recrystallization. It raises this important question. What's truly the optimal temperature strategy for robust and complete breakdown? Maybe it's not just about speed.
Fascinating trade-off. Okay, so that's bottles. But what about the really tough stuff, the fibers and blends? You said that's where mechanical recycling fails.
Exactly. This is the ultimate challenge. Separating PE from cotton or polyurethane in a fabric is incredibly difficult, almost impossible mechanically. It's like trying to unbake a cake, as you said.
So how did the enzymes do here? They tested PET214M6 hot and LCC-ICCG on fibers.
They did. And the results were quite telling. For pure peat fiber and also for PET cotton blended fiber.
A really common blend.
Yeah. PT214M6 hot actually performed better at 60 degrees Celsius than LCC-ICCG did at the higher 70 degrees Celsius.
Better at a lower temperature again.
Yes. And what's really fascinating about the PET cotton results is they clearly suggest the enzymes selectively degraded only the PT. That cotton fibers were left intact.
Wow, so they're like super specific Pac-Men just eating the PT.
Exactly. It showcases their incredibly high substrate specificity. They know exactly what they're supposed to eat and leave the rest alone. That's crucial for recycling blends. You want the PT polymers back, but maybe you also want to recover the cotton.
Okay, that's impressive. What about other blends, like with stretchy stuff?
The PTPU blend, that's PTT with polyurethane, spandex, lycra, that kind of thing.
Right.
Here they found something really surprising. These blended fibers were only degraded effectively at 50 degrees Celsius by both enzymes.
Only at 50, not higher.
No. They specifically noted that degradation didn't work well at the higher temperatures they tested, like 60 or 70 degrees Celsius.
That seems counterintuitive. Why would lower temperature be better?
It puzzled them, too, initially. But it connects back to that glass transition temperature idea. The 2G, polyurethane's 2G, is around 55 degrees Celsius.
So right between 50 and 60.
Exactly. So at the higher temperatures, 60 or 70, the polyurethane component in the blend starts to rearrange itself, possibly flowing or changing shape on a microscopic level.
Making it harder for the enzyme to get to the PET.
Precisely. It likely reduces the accessible surface area of the PET that the enzyme can actually reach and attack. It's like the polyurethane melts slightly and shields the PET.
Wow, so you have to keep the whole blend below the TUJ of its most sensitive component.
That seems to be the critical insight here. The reaction temperature needs to be carefully chosen based on the properties of all the materials present in the blend, not just the target PET. It's like cooking a delicate sauce. Too much heat ruins it, even if one ingredient could take more.
That's a really crucial detail for handling real-world waste streams, which are always going to be mixed.
Absolutely. It adds another layer of complexity, but also understanding.
Okay, so wrapping this up, this deep dive has really shown a major leap forward in enzymatic plastic recycling, hasn't it?
I think so, yes.
The creation of this PT221M enzyme with that huge 28.6-fold activity increase, plus the successful large-scale production. It feels like it offers a powerful new tool in our fight against plastic waste. It's moving beyond just lab potential.
Definitely. And just to distill those key advantages again, the PT2 variants show real effectiveness at moderate temperatures, around 60 degrees Celsius, which is great for energy efficiency.
Right.
They show particular promise for those really challenging pure and blended PT fibers, thanks to that incredible specificity just eating the PDT.
Leaving the cotton alone.
Exactly. And their superior performance at lower enzyme loadings compared to some established enzymes like LCC-ICCG is a massive potential win for making this economically viable on a large scale.
Cheaper processing.
Potentially, yes. And, maybe most critically, this work has really underscored the crucial insight about reaction temperature needing to be tuned to the properties of the entire polymer blend, especially considering things like the glass transition temperature of all components. It's subtle, but really powerful for practical application.
So thinking bigger picture then, a final thought for you, our listener, to mull over. If advancements like this continue, how might this kind of enzyme engineering reshape whole industries, like fashion, packaging? Could it genuinely move us towards a truly circular economy for plastics?
It's the big hope, isn't it?
It is. And maybe even further out. What new frontiers might open up for designing materials and recycling processes together from the start, making them inherently more compatible, maybe designing future waste challenges right out of existence? Something to chew on.